Hello, my name is Jonathan George. My semester project for ECE 561 explored tracking cars through TPMS. I'll be talking about how tire pressure sensors in our cars can be monitored using software-defined radios. First, a quick shout out to my friend and ex-coworker Alex Wilson, who is not a student in this class. The idea for this project comes from conversations with him. He let me borrow his radios and kept me company during some of the experiments. He also helped me debug some of the radio issues I ran into. The project experiments, the write-up, and presentation are all done by me. Wireless signals surround us in modern life. Many of the technologies which give us great conveniences take advantage of wireless communication. Many people will think of their phones or home Wi-Fi when they think of wireless security or privacy issues. More recently, the Internet of Things has made people consider what happens if their fridge or other smart home device was hacked. However, most people wouldn't have thought about their car's tire pressure sensor as something which might be used to track their movement. Tire pressure monitoring systems, or TPMS, monitor the tire pressure and temperature of our car's tires. This information is broadcast over 315 megahertz radio frequency. With these tiny batteries, most TPMS can last for 7 to 10 years. TPMS is very convenient since it allows us to not have to constantly check our tire pressure, which helps us keep us safe and improves our gas mileage and battery range of our car. Being wireless means there doesn't need to be a hardwired connection between the spinning tires and the car's central computer. In order for your car to know that the TPMS broadcasts it receives from your tires are actually from your tires, there's a unique ID field that's sent with the broadcast. Unfortunately, TPMS doesn't use any kind of encryption, which means anyone with a 315 megahertz receiver can decode any car's TPMS broadcast. Is that such a concern? Let's go over a few possibilities. Here are a couple of the questions that I thought of when I heard about this TPMS broadcasting. Could we use these unique IDs to track vehicles at intersections or parking lots? Would it be useful for cities to gather traffic statistics? What is the range of a TPMS radio and how often does it broadcast? Here are a couple other questions around security and privacy. Could companies use TPMS to correlate consumer behavior by tracking which parking lots they visit? Could the government use TPMS to track citizen movement around the city, maybe to track down criminals or terrorists? Could criminals use TPMS to track my schedule and figure out when I'm home and when I'm at work? In this section, I'm going to go over some of the hardware and software that I used for this project. For this project, I used the following hardware: a Raspberry Pi 3B, an SDR software-defined radio, and a HackRF software-defined radio. Most people are familiar with Raspberry Pi, so I'll just discuss how I used the Raspberry Pi when I discuss my experimental setup. First, I'll go more into these software-defined radios. SDR and HackRF1 are SDR radios, which can receive a variety of frequencies depending on the software program you are using. The SDR is much cheaper and has a small form factor which could be used in an embedded device. The SDR was the primary radio I used for this project. The HackRF is much more expensive and is a higher-end SDR radio, which is more designed for lab tool prototyping. I mainly used the HackRF to help debug when something went wrong with the SDR radio. Again, a big thanks to Alex for letting me borrow his radios. I also used several software applications for this project. GQRX and Cubic SDR are both open source SDR receiver applications. They let you interact with an SDR to set the frequency and get a visual view into what the radio is seeing. You can even listen to FM radio using them. I use these programs to debug the radios and record specific broadcasts of interest. RTL433 is the primary software I used. This open source project is designed to decode various common RF signals at multiple frequencies, including thermometers, security systems, barbecues, and importantly, TPMS. My impression is that this application is primarily aimed at home automation uses. In the picture, you can see an example output of several TPMS broadcasts from a Toyota, including the ID, temperature, and pressure information. Not only is the software open source, but the device encodings are also crowdsourced. I quickly noticed that RTL433 didn't pick up my Nissan Leaf's TPMS. It was easy to add support to RTL433 to correct this. The image at the bottom is a fast Fourier transform view of my Nissan's TPMS broadcasts. Using RTL433 to debug the failed decoding, Alex and I were able to determine what the preamble, ID, and pressure fields were. The result was a new device decoding C file, as shown on this slide. And here's the result. You can see that it looks like my tire pressure is even a little bit low. Alex submitted a merge request with the project to add this new device to the main tree. In this section, I'll go over some of the experiments I did using RTL433, the Raspberry Pi, and the SDR radio. My main home setup involved a Raspberry Pi and SDR running RTL433. The goal here was to see what I could listen to from my living room. The Raspberry Pi was mainly used for convenience since I could leave it alone and SSH into it when I wanted to view the results. I was surprised at how well I could listen to the street even from inside my house. Since RTL433 let me dump directly into CSV, it was easy to process the data later in Excel. Here are some of the results. This graph shows a timeline of 1 week's worth of TPMS signals which RTL433 decoded. Each row in the graph represents a unique TPMS ID captured. About 200 unique IDs were seen over this week-long period, and the chart shows how often each was seen. You can see that there are some extremely noisy TPMS signals at the bottom and the top. Some TPMS seem to go off at a regular frequency, regardless of moving, which makes it clear when the car is home. It's also worth remembering that RTL433 isn't perfect. There are likely more TPMS decoding schemes missing, or even some incorrect ones. The next experiment tried to answer some of the more basic questions about TPMS devices. Since TPMS used their accelerometer to decide when to broadcast, I needed to simulate a car driving around. I did this by using an old TPMS and a house fan. To make sure nobody got hurt if something flew off, I put it in a cardboard box as shown. The result let me turn on the TPMS on demand and measure the frequency and range. This experiment showed me that when a TPMS first detects acceleration, it begins to transmit roughly once per minute. After about 20 minutes of this, it slows to be less frequent. I assume this slowdown is to conserve the TPMS's battery. This was very inconvenient while trying to determine the broadcasting range. Still, I determined that the good range of this old TPMS was around 25 feet. After that point, the radio would sometimes fail to decode the TPMS broadcast. I saw TPMS broadcasts from further away during other experiments, so I'm sure this varies between brands and battery life. The final experiment was on the side of a busy road in South Fort Collins. Here I attempted to see what % of the cars driving by could be picked up by the SDR radio. Alex came along to help me count. We were only able to pick up about 5% of the cars driving by. At first, I was disappointed by this result, but I reasoned later that there are a few limiting factors to our setup. First, likely many of the cars driving by were unsupported by RTL433. Second, we were pretty far from the center of the road. The best place to monitor would have been an intersection or parking lot, but this also would have made counting harder. Now that we've learned a little bit more about TPMS and done some experiments, let's revisit my original questions. Can we track cars using TPMS at intersections and parking lots? Yes. With many monitoring points and a better setup than I had, then someone could track individual TPMS IDs as the drivers drive around. How about traffic statistics? Based on my experiments, a radar at intersections would probably be more accurate. And as answered from my fan in the box and home monitoring experiment, there seems to be quite a variety in terms of both range and time between broadcasts. How about our more serious privacy and security questions? It seems possible for a company to track which car visits which parking lot. How useful would this data be? maybe not enough to be worth the cost without a way to correlate it further. Could a government use TPMS to track movement? It certainly seems possible. Perhaps TPMS recordings could be used with camera footage to determine what TPMS ID corresponds to a suspect's car. Then, using TPMS recordings from across the city, the suspect's location could be narrowed down. This scenario seems plausible, but unlikely without a lot of infrastructure and technology. Plus, with the advances of facial recognition, it might not be the biggest risk to our privacy. Finally, could a criminal monitor a home to determine when the best time to break in would be? Without knowing the exact TPMS IDs of their target, then it would be hard to do this in a busy neighborhood with the amount of traffic that I saw. Where can we go next? We could enhance my home Raspberry Pi setup to notify if my tire's pressure is too low. We could also explore other RF devices, such as those used in home automation, like wireless thermometers or security systems. We could also explore the RF security of devices like garage doors and key fobs. This is something that Alex has looked at a little bit, where he's actually recorded and replayed his garage door and key fob to unlock his house or his car. We also could keep looking into the previous questions further. There's a lot of details which I didn't get to, but I could have answered more if I had more time. So, in the end, I had a lot of fun playing with radios and learned a lot about how TPMS radios work. I hope you enjoyed my presentation.